Hi, in this short video I hope to explain to you how processes, structures and drivers interrelate within socio-technical systems and why understanding these concepts is key to the art of systems engineering. I hope you agree after watching this video. Before showing some examples, I will define the concepts of system, process, structure and driver. A system is some part of the universe that we happen to be interested in. By process, we mean some part of a system that is dynamic, a part that changes its position, its shape, or any other property. So, process captures the idea of change over time. In contrast, a structure is a subsystem that is static, a part that does not change over time. But note that this is relative. This plastic bag is flexible, so its shape changes as I manipulate it. But even so, the plastic bag is the structure that contains and shapes the hydraulic processes of the water it contains. So if you like, you can think of structures as slow processes, subsystems that change only little relative to the processes that they shape. By driver, we mean the cause of change. My hand motion was driving the bag's shape change, and that change was driving the water flows inside. So, fundamentally, structures and drivers are processes. Processes are the universal building blocks for engineers. But differentiating between processes, structures and drivers will help us in our thinking about systems engineering and design. Systems engineers design structures to shape processes so that these better serve human needs. But engineering always takes place in the context of some larger system. So let's first take a look at some natural processes on our planet Earth. We could see solar energy as the driver for the evaporation process, differences in air pressure as the driver for wind, and then wind as the driver for the cloud movements that transport water vapor until it condenses to drops that are so large that gravity makes them fall to the surface again. Gravity not only drives the precipitation process, but also the water flow in a stream. This water flow process is evidently shaped by a structure, the riverbed. But on a timescale of hundreds of thousands of years, we could also view the water flow as the driver of the erosion process that changes the shape of the riverbed. Now let's turn to artificial structures, created by engineers to shape water flows to serve a human need.
To generate hydroelectric energy, you need two things: an abundant supply of water and an elevation to drop it from. Building a dam creates both. The dam creates a reservoir which stores water until it's ready to use. Water enters the generating system through a series of giant intake pipes. It then travels down a steep pipe called a penstock, creating a massive column of water with a huge amount of force. At the base of the penstock, the water passes through a turbine. The giant blades rotate the drive shaft in the turbine, which is connected to a large generator. This converts the mechanical energy into electricity. The electricity travels along high-voltage wires to transformers, then onto transmission towers, where it connects into the provincial power grid. After passing through the turbine, the water continues through the tail race, where it rejoins the river below. A hydroelectric dam is a remarkably simple, sustainable, and clean way to generate huge amounts of power.
Now, let's review this example in terms of processes, structures and drivers. The reservoir fills with water because the hillsides and the dam shape the river water flow. The dam structure holds the pipes, penstocks, turbines and generators in place. The intake pipes regulate the river water flow into the penstocks. Driven by gravity, the water flow is conducted by these penstocks into the turbines. Inside the turbine, the massive water flow spins the runner. Its spinning shaft, firmly held in place by bearings, spins the generator's magnetic rotor inside its stator, converting mechanical energy into alternating electric current. Transformers then turn this electricity to high voltage power, which is then fed into the power lines carried high above the ground by transmission towers. The transmission grid can transport the generated power over great distance to places where it serves as driver for countless processes, such as lighting, heating, transport and communication. Meanwhile, transmission grid operators have to balance demand and supply. As millions of people switch their lights and electric appliances on and off, thousands of generators must exactly match the load. To achieve this, power companies forecast loads and buy electricity on the day-ahead market and on the spot market, while grid operators contract balancing power to compensate the forecasting errors. These social processes of forecasting and planning, of trading and settling transactions, are shaped by social structures that we call institutions. Institutions are intangible, but laws, regulations, contracts, and organizations and procedures structure social processes as surely as dams, pipes, and turbines shape physical processes. We can also identify drivers for social processes. Institutions like market regulations and contracts create economic incentives and obligations that make people act on information such as market prices, forecasts, and deadlines. And here too, we see processes that create drivers for other processes. Guided by long-term objectives and constraints, grid operators make maintenance plans. And then these plans structure the operational process of maintenance and repair such that workers will do what is needed on time to ensure that the physical structures remain functional. So, structures shape processes. They can be natural or human-made. We can use natural structures like hills and rocks as structural elements supporting artificial structures like dams and transmission towers. But structures can also be intangible. The physical structures and processes in our brains allow us to think and communicate. Social processes that over thousands of years have shaped cultures, societies, and technologies as slowly and surely as rivers shape their riverbeds. The world has evolved into an infinitely complex socio-technical system. Any artifact will function only if its design is compatible with the physical and social structures that form its context. As systems engineers, we can only make small changes. But small changes can make big differences. That is why we analyze and design, to create structures that will shape processes so as to improve the overall performance of the system we are part of. Small things matter. A well-designed fuse protects the integrity of the entire grid.